Hello. Good afternoon, everybody. My name is Nimish Hathi, and I will be chairing this session. This is session 3A, focusing on CGM and IGM. And first, we have a review talk from Sanj Borthaker from Arizona State.
All right. First of all, thanks for having me here. It's such a wonderful conference. I've been really enjoying. And this is, I feel like it's really appropriate because every time I write a proposal on CGM, IGM, I'm motivated like, what can CGM, IGM tell us about star formation? So you're the right people that, our research is kind of trying to figure out certain things, how gas flows in and out and how CGM can help. So today I'm going to take a stab at it. Initially, I thought I would probably give a little bit of review, but I got very excited about certain things I heard in the conference. So I just picked and chose certain things that I think might interest you. So it's not a review talk. I won't be actually referring to some of the very interesting things going on in our field, but we have very many speakers talking about CGM, IGM. So you have many opportunities. So let me start with this, So CGM, IGM is actually your friend. This is really supporting star formation in the centers of galaxies. There's very little star formation going in CGM or IGM, but processes that go in these big arenas really help star formation and sometimes regulate star formation. So to motivate that, one of the primary things we need for star formation is fuel. And galaxies, in general, have gas, but they are consuming it at a very large rate. So most of the time, in few giga-years' time, the gas would be over, but we're continuously seeing that these galaxies have gas, so we need a feeding process. Otherwise, star formation would shut down in the long run. We also lots of people talked about wonderful results on metallicity. You could see metallicity gradient. People have done chemical evolution. So if you have these processes, then you really have to understand how gas is coming from and how gas is getting out of your system, how the metals are circulated. And this is just showing the G-dwarf problem, saying that you do need gas to come in, and that's where CGM and IGM plays a role. Related is the mass metallicity relationship. So a closed box model would not produce a mass metallicity relationship, which is it's a very important part of our galaxy evolution understanding. But ultimately, when we have this picture of gas coming in and out, if you look at it, everything outside the disk is the CGM, and then beyond that is the intergalactic medium. So really to complete the cycle and to understand what's going on, all the beautiful outflows you see, what happens to them? We have to figure out what goes on in the CGM. Other things, we could look at the metal budget. Metals are missing from the disk. And we also have, in general, the mass budget, because the circumgalactic medium is 99.99% of the galaxy. So it's basically entire galaxy minus the disk, right? So by volume, it's so much that even though it's very low density, it adds up. And essentially, it is a very big mass reservoir comparable to the mass of the stars. And finally, which I'm going to stress more in the talk, is that these systems really hold information of these processes that go into feed the galaxy or from outflow, so we can find signatures of inflow, outflow for much longer time to really understand the processes. And that's kind of what is very, very important. And there are different ways of figuring out metallicity, ionization state, kinematics, and other things. But essentially, this is a way of understanding small-scale physics using this big volume media. So before I dive into CGM, there are two very prominent ways that you can actually study the CGM, either in emission or in absorption. I'm mostly focusing in the absorption side, and emission side is talked by other folks here. But when you're looking at absorption, we love it because we're very, very sensitive. We are looking at gas at 10 power of 13 centimeter per square centimeter, so that's the column density. Very different from what in 21 centimeter emission map of the order of 18 or 19 would show. But we are limited by the background source. And when you do a background source, you can't just pick any galaxy, so we have to do a sample selection very carefully. But in addition to that, I do want to show the difference between what we do. We look at a background source that probe material in the CGM, so we might be looking at multiple clouds at multiple distances and their kinematics. And to distinguish it from other absorption studies that look down the barrel from the galaxy, we do not have the luxury of just using blue shift as outflow, because it could be blue shift as inflow, things going towards the disk, or red shift, things going towards the disk. So just having blue or red doesn't tell us inflow or outflow. But we have ways to figure that out, and there are people do modeling to figure out some of the kinematics. But without going into detail, the two things to remember is that we are very, very sensitive to gas at huge column density range. And the other thing is when you have an absorption spectroscopy, you could have multiple CGM clouds coming in at different redshifts. You're redshift independent. So now that we have sort of put our ground rules, I want to just jump into some of the results from the intergalactic medium. I will try to start with intergalactic medium and sort of zoom in. Again, this is not a review talk. There is a lot of work. I possibly cannot fit everything in even 25 minutes, but I'm going to spend only 2 minutes on intergalactic medium. But I wanted to sort of point this result from almost 2 decades back. This is the galaxy absorber cross-correlation function, which is just saying that what's the probability of finding an absorber, in this case Lyman alpha, so that's just neutral hydrogen, when you have a galaxy. And what these two studies found is that you see a very strong correlation between 21 centimeter detected galaxies, so these are gas-rich galaxies. This from Ryan Weber and Shellen Chen found that you see a very strong correlation with emission line galaxies. So these are star-forming H2 region present galaxies. Qualitatively, they are consistent. Gas-rich galaxies are star-forming galaxies. But the problem is that, is it mostly outflow-driven or inflow-driven? And to see this, people have actually done many, I'm just listing some of the other people who have done a lot of work and might have missed some. Pardon me for that. But I want to sort of put this in context. So here is an example of the cross-correlation function. It's just showing in one dimension, but nevertheless, it's kind of clear. If I just have the same sample of galaxies where I have 21 centimeter information as well as their emission line information and colors, what I see is that the H1 galaxy shows the strongest correlation with gas outside in the intergalactic medium. It's not a direct proof that things are falling in, but clearly it shows that gas-rich galaxies are surrounded by gas-rich environments. And these need not be necessarily extreme star forming at this time. Following back to the CGM, so now that we know the environments are rich, we can actually look at the circumgalactic medium as a function of gas mass. So here is a stack for 4 bins of 21 centimeter ISM mass, H1, so less than 9.10 in log scale up to around 10. And what we see is that these stacks clearly show that you have more material in the CGM if you have more material in the disk, in the neutral phase. And that is interesting because the disk is about 20 kiloparsec and the CGM is 250, 300 kiloparsec. So we are talking an order of magnitude in difference. And the way we interpret is something like this, clouds in the sky, just kind of a covering fraction argument because we are stacking these. And this is sort of fits in with the IGM picture as well. Now that we know the environment, the main question that we are really interested in, how do we get this gas into the disk to form stars? And primarily, we have two methods. Either we can go along the disk, somewhere join the disk at very large galactocentric radius and sort of move inwards, or just fall into the disk from above. And we find that there are good examples of both of these processes acting as we look at different galaxies. So I want to introduce you quickly to a survey that we are conducting. It's called the DISC survey. I do not have a lot of imagination. We're studying DISC, so we call it DISC. But anyways, a postdoc came up with this acronym, thanks to Hansen Kim. But the idea is that we look at this very nearby galaxies where we can see very detailed structure of what the stars are doing, what the gas is doing. 21 centimeter emission maps exist, and we can study the circumgalactic medium. So the first thing I want to show is that we do find these large co-rotating disks beyond the disk that's seen in 21 centimeter, and that's probably because the surface brightness drops. So here is the quasar. Here's an example galaxy. And of course, we have the 21 centimeter map, so we have very nice measurement of velocity of how the disk is rotating. But if I look at the quasar, I have metal lines, many more, but I'm just showing one. And what I could do is I could just trace the velocity from the disk, and then there's a gap, and then to the quasar. Oh, that's Hansen Gim. Well, this is not how he got the measurements, but you know. Might find something else, but we have to contend with it for now. So what we find is that the gas at this point is co-rotating with the disk, so we think it's a bigger disk. And we repeated this for 35 galaxies, and we pretty much found the same thing. This is not a revolutionary idea because people have seen co-rotating disks, but with limited, they didn't have 21 centimeter gas. So they're looking at the stars, CAPSAC, and all these other people, but also simulations, which I'm not covering. Again, a very big part of CGM studies, simulations, which we'll talk later on, show these large rotating disks. So we are eventually sort of seeing the stuff that people are seeing in simulations. All right. So that's for the radial motion. That's what we think, that maybe there is material, they might be coming in. The other method is to something that falls into the disk. And here is an example. Some of you might know this galaxy very well, better than me. It's M61, very well studied galaxies. The 21 centimeter contours are shown. The optical part is there. And again, we have very good measurement of velocity where the position of the quasar is. So we get ISM. The scales are very different for the ISM plot and the CGM plot. But in the CGM, what we see is that we see the ISM structure in all sorts of metal lines and hydrogen. But we also see another cloud, which is metal rich, 345 kilometers offset. And this is typically, if you see something like this in the Milky Way, we'll call it high velocity cloud. Now, so the first thing is that Milky Way kind of structures exist in other galaxies. That's wonderful. The other thing is that what is causing this? And I can talk this in later detail, but what we think is this is not outflow because this galaxy is not super star forming. The quasar is in the wrong position. So for an outflow to have a 345 kilometers per second projected, it has to have like 700 kilometers per second outflow, which we don't see it at all here. So we believe that this must be infalling material. And that's kind of very easy to explain. If you have something that, you know, a halo and you leave something, it just falls ballistically. So it can reach velocities compared to a circular velocity. So that's what we think is going on. And this material would just land on the disk. In certain cases, we find both the co-rotating disk and these non-co-rotating, infalling, outflowing structure. This is another galaxy, NGC 3344. I'm not going to go into details again here because of lack of time, but I'm just trying to illustrate the fact that all these galaxies show very similar things, that we see a co-rotating component right here where the quasar is in this direction. So it's co-rotating right with this gas. I love this image. This is a digression. Just to show off my beam size, because I hardly get to see it. Now, if you can't see it, it's because my data is that good. Anyways, but the next step is, now that these big co-rotating disks exist, we don't have to take the word for it that these might be feeding us. We can actually model them. Oops, what is going on? Okay. We can actually model them with tilted ring models, and we actually see that there is, at the position where the stellar disks end, we see this big velocity offset. There's this inflow and outflow, radially flow into that area where there's star formation also going on. We also see that warps are forming. So there's a lot of different things that we can actually do. But now what I would like to sort of summarize here is that I showed you evidence of existence of a large disk, and also that we see velocity that's showing it's radially inflowing. And then, of course, I showed you things that are falling from above. So I think what is happening is that both radial process inflow as well as things that might have come out of the disk, high metallicity gas that stays in the CGM for some time, cools the CGM, now becomes a bigger, cooler cloud, falls in. That's what we saw in the previous example. Okay, this is all well and good, but you guys study star formation, and I wanted to show what can your studies tell us, and how can we inform you. So I want to give you a slight digression and an example of one of my galaxies, which we've been studying the metallicity as a function of galactocentric radius. So this is the gradient, all well and good, but we see these H2 regions that have lower metallicity than what you would expect based on the general trend. Interestingly, they also show velocity offset from the 21 centimeter disk. And what we believe is that these might be the H2 regions that were produced by recent gas accretion. You need not always have it in low metallicity. Sometimes you do see velocity offsets in normal metallicity gas, which is okay, because if it's recycling, it is metallicity rich. But any of these examples really help us understand what might be driving the inflow process and what's the real mechanism that might be feeding the galaxy. So things like that are really, really helpful for us that you guys can provide. This is just to show that when we do a chemical evolution process, we find a bizarre mass loading factor that shows that it should increase as function of radius. Nothing wrong with the calculation. It's just that our inflows are much more dominant than outflows, so the model basically, eta, takes care of the dilution factor here. Anyways, there will be a paper out by my student Alejandro Alvera, and you can look into that more. Okay, I'm running out of time, so I also try to talk about impact. Now that we have sort of talked about inflow and gas coming in and supporting star formation, we want to talk about how star formation is regulated, and that brings us to feedback. So one of the things is that clearly the outflows are going out, and you could deposit matter in the circumgalactic medium. The other thing is that although there might not be enough matter, there is wind fluid and radiation that can change the state of the circumgalactic medium. And I'm going to focus more on this. And this has been seen early on with STIS, and then COS. This is COS halos. This is COS bursts. COS bursts is starburst galaxies control our normal galaxies. So clearly in carbon-4, you can see that they have much higher carbon-4 versus other galaxies. This is an oxygen-6 plot, and yeah, so on and so forth. There has been a lot of work. I would have filled up the whole slide, so pardon me if I have missed your favorite. But we think that this is kind of an indication that shows that there is something going on. And I want to give one specific example from the COS burst survey. So this is a galaxy, that's the quasar, very far, about 80 kpc or so. And what we see here is a special case where we see hydrogen, cooler gas. I just color-coded it with ionization state. Cool, this is cold, this is hot. Actually, it's reversed, my apologies. So then we have the intermediate ionization state, and then there is this very high ionization state where there is no hydrogen or any other lower ionization states detected. So we are seeing these multi-phase outflows that is just because our sight line crosses through something like this, a cone where you have clouds of different ionization states. So we can do this very detailed modeling with the data we have at this time, and we haven't done it yet, but I think stay tuned, and it's really interesting to see what happens to all the outflows, where they end up. Before I try to end my talk and talk about habitable worlds, I do want to mention another survey. It's ongoing. It's a HST large survey. It's called Cost Magic. And the idea is to just understand what goes on in the circumgalactic medium, what is the microphysics as the wind goes through it. And we use this plot, motivated by work by Andy Fox here, who has done this for Milky Way and others, where this is our BPT diagram equivalent. So it's a ratio plot of nitrogen 5, oxygen 6, and carbon 4 and oxygen 6. But the cool thing about it is that different processes land at different positions. So this is, you have collision ionization, you have photoionization, and when we put our points, we see that most of them lie in this band, in this red zone, which is conductive interfaces, so which is basically conduction between phases. There's magnetic fields, so the various different models predict different parameter space. But very preliminary results show that these galaxies are actually showing that something hot is moving through the cooler clouds in the ice. At 3 minutes, okay. Just to, this is Brad's work. Brad also had a paper on IgM out where we have only 5 sight lines because it's very difficult to have oxygen 6 and carbon 4 in the Gauss bandpass. So there are not many intergalactic medium sight lines, but even in intergalactic medium we find that there are these conductive interfaces. And sometimes we just can't explain what's going on. So, you know, good news for us. We have more work to do. All right, so I have 2.5 minutes, so I want to look towards the future and talk about habitable worlds. And I want to pose 2 big questions that I think are quite important in understanding how galaxies are evolving, both in terms of star formation and galaxy growth. So one of the things that we know so well is the disks of galaxies, but our understanding stops mostly at the stellar disk, where beyond that we can't have good measurements of metallicity, and sometimes up to the 21 centimeter disk. But really what's going on beyond it is driving what's happening inside of the stellar disk. And we really need to know what's the masses, what's the metal content, and that'll be really interesting. It'll be really interesting to see if the gas disk has the same metallicity distribution, the same radial profiles in metallicity as you see in the stellar disk. The other thing that I would say is that we need to see these signatures of interactions. For that, we need higher ionization transitions and many more sources. So I'll start with my favorites. So what we need to do is we need to sort of get to a stage that where we have expanded our sight lines, which is a big limitations for such studies. So here are some diagrams from LUVOIR, but you could think of it as habitable worlds, but this is an 8-meter class, will really get you, now look at, based on Hubble, we hardly can go to very high redshifts, then of course 4-meter class, but 8-meter class onwards, we can really probe higher redshift where even high energy lines are within our range. We can also do neonate or other lines, things like that, which are very important. And the UV range is extremely important because the density of lines are just crazy here versus optical. No offense, I mean, it's really wonderful here. But in this case, so many. So essentially, if you want to trace different types of material, you really need a 600 angstrom bandpass here is really powerful. I don't know, I'm just going to drive this point. This is with Hubble, with a couple of orbits today. With Hubble, we could do, for a 19th magnitude quasar, we could do all these lines at all these column densities. Oops, I'm out of time. But the point is that we want to do it for 21st magnitude. Then we will have so many more. So I'll leave my habitable world slides here, which I have already covered, and I'll take questions. Thank you.
Short comment then a question. The first comment is that in our own galaxy, from high velocity clouds, we know has been coming from the Magellan stream. It is estimated 1 solar mass per year of injection. And actually it has been proposed that the path that the Orion star formation region has been formed out of the impact of the Magellan stream galaxy center region. And my question is, what is your opinion about the formation of the first galaxies, the most massive galaxies and black holes, due to the streaming cosmic streams that are claimed to some of them are impinging into dark matter halo, massive dark matter.
Thanks for the question. I don't think I am in the best position to comment on very high redshift first galaxies, but I'll take my stab because I'm here. Yes, I agree that it must be these streams, but at that point we don't have the kind of circumgalactic medium that we have it today. So I think it might have been much easier for gas to come into the very centers. So we do expect, based on what my simulation friends tell me, that we do expect that things must be like swirling around and forming somewhat of a disk, but probably not a good disk, and forming the first galaxies. But once they are morphologically like a spiral galaxy, I think we have to sort of think about recycling processes much more carefully.
So you had a nice plot where you showed how the properties of the CGM changed as you went to more gas-rich galaxies. But of course, your sightlines are also at different radii. What happens if you look at the CGM as a function of radius instead of as a function of mass?
Yes, that's a very good question. So yes, the biggest parameter that you need to, we see is the distance. So the most important, if you don't know anything about the galaxy, if you just know how far it is from the galaxy, you can predict. So when, that slide probably didn't show it, we also binned it with distance, similar distance. And we did some statistical analysis, so it's a second order effect. Yes. Thank you for bringing that up, appreciate it.
Just one last question.
Might be a very naive question, but like a similar question along those lines. So if you have like a galaxy with like, inflows and outflows together at the same time, and if you have like, let's say just a few sight lines, would you be able to differentiate between that, and how much information would you be able to extract?
Yeah, so we are always struggling. Individually we cannot. Statistically we can. So if it's just one sight line, I cannot well, sometimes I say it's probably inflow because of other arguments, but in general, it's very difficult to say. But statistically, we also identify samples that where we think the outflows might be prominent or inflows might be prominent or stable state is more prominent. So based on the star formation rate, gas mass, stellar mass, etc., and the position of the quasar. But we do it statistically, and that's why we need a bigger telescope so that we have many more sight lines to sample the parameter space properly. Thank you.
Let's thank the speaker again.
Can you change the slides also?
Yeah.
No? All right, okay.
So our next speaker is Shapna Mishra from STSCI, and she'll talk about cool CGM, the LMC.
Yeah, thanks, Sanj, for the nice review on the importance of the CGM. So let's start this contributed session with the CGM of our nearest neighbor. Yeah, so shown here, can I just remove this? All right. Yeah, shown here is the schematics of our local interacting group with marked location of the relative position of Milky Way, LMC, and SMC. This system is actually melting pot of the plethora of interesting processes happening in our local group. This is the closest known system with colliding CGM. The interaction between the Milky Way and the Magellanic Cloud leads to the formation of a trailing stream of gas known as the Magellanic Stream. All right, that's fine. Why it's not? Oh, it's because of this. Okay. So the origin of this Magellanic Stream is traditionally been explained using two competing models. The first model is the tidal model, which says that the stream is originated due to the tidal interaction between the Milky Way and the Magellanic Cloud during their first infalling passage. And the second model is drag model, which says that the streams are originated because of the ram pressure stripping of the Magellanic gas by the dense Milky Way CGM. However, both these models, they consider LMC as a dwarf satellite galaxy with lacking surrounding CGM. But thanks to the recent development, now that we know that LMC has a typical halo mass of 10 to the power 11 solar mass, which is enough to hold its own CGM. And also these two models could not properly explain the high ionized gas mass of 10 to the power 9 solar mass in the stream. So very recently, looking at all included an additional component known as Magellanic corona in their simulation models. So after including this component in their model, they could properly reproduce the high ionized gas mass in this stream, while also accounting for the large LMC halo mass. So if at all LMC do have CGM, and as also pointed out by the Sanj, that it will be very crucial for the inflow and outflow of the gas around our local group. So indeed, in the recent study by Krishna Rao 2022, the authors indeed found the first observational signature of the Magellanic corona. So what they have found the declining radial profile of collisionally excited gas as traced by C4, Si4, and O6 as the distance from the LMC increases. So this is the typical signature of a bound CGM of a galaxy. And the temperature of this volume filling warm hot phase was found roughly 10 to the power 5.3 to 5.5 Kelvin. So while this is really interesting, the cool phase of the LMC CGM has still never been explored. So motivated by this, we revisited the sample of Krishna Rao 2022 of 28 quasar sightlines. and probing LMC far up to 35 kpc distance, and having HST cos spectra available. So here what is shown is the location of these 28 quasar sight lines in the galactic coordinate around the LMC, and they are also color coded with their distance from the LMC. And for visual, I have also shown the H1 emission column density map taken from the Westmeyer study. All right, so next what we did, we fitted 15 UV absorption line of 7 low ions in all these 28 quasar sight lines. And for example, I'm showing the result of our fitting for one of the ion SI2 1526 for this quasar sight line, which is at roughly 8.1 kpc distance from the LMC. And we only focus on the absorption component, which are beyond 150 kilometers per second, so as to avoid the contamination from the Milky Way. Yeah, after this fitting, we measured the absorption line properties such that number of component, column density, and velocity centroid for all these absorbers in 28 quasar sight lines. All right, so shown here is the radial profile of 4 of our low ions. So in each, as identified by the labels at the bottom left corner of each panel. So on the y-axis in each panel, we show the total column density of these low ion, and as a function of impact parameter on the x-axis, the solid filled circles are showing the detection, while the data points with upward arrow, they shows the saturated lines where they show the lower limit from the saturated lines, and the arrows pointing downwards shows the upper limit from the non-detections. Then in all the radial profile, we fitted power law using censored Monte Carlo linear regression, which takes into account both the lower and upper limit in our data point. So as can be seen that all the radial profile belonging to all these 4 low ions, they are following the declining radial profile with consistent slope of the power law. So which says that LMC does has its cool CGM, and which is multi-phase when it combined with the high ion results. Next, we explored how this cool gas is distributed around the LMC. So what is plotted here is the normalized, the number of component normalized by the quasar sight line for the 3 increasing bins of impact parameter. So in each, all the low ions, you see, once you are moving closer towards the LMC, the number of complexes are increasing. So which says that the inner CGM of the LMC is complex. All right, next we explored the kinematics of the cool gas around the LMC. So to do that, what is plotted here is the column density weighted velocity centroid of the low ions as a function of impact parameter, LMC impact parameter. So very interestingly, in each panel, you can see, and this horizontal dashed line is the velocity of the LMC belonging to 80 kilometer per second, and this gray band represents the plus minus 50 kilometer per second around the LMC. So very interesting, beyond 18 kpc, which is marked by this vertical dashed line in each panel, all the beyond 18 kpc, this cool gas is from all the ions is preferentially found at the lower velocity. However, within 18 kpc, this gas is randomly distributed around the LMC velocity. So what does this mean? All right, so this means that the gas which is beyond 18 kpc may not be associated with the LMC CGM. It may be associated with the strip gas coming from the stream, which leaves us with a very interesting finding, which says that LMC CGM is only extending up to 18 kpc, which is 10% of its virial radii. So talking in terms of an isolated galaxy, this would be the smallest known CGM possible. But we know that LMC is not the isolated galaxy. It is actually an interacting galaxy. So we infer this, that this compactness of this LMC CGM, or you call the truncation of this LMC CGM, is because by the it's in strong interaction with the Milky Way. So again, to explore this, how this ionized gas is correlating with the neutral gas, H1 neutral gas coming from the stream. So what we have plotted here is we use the velocity map of H1 emission from the Westmeyer study, and we divided our agent sample into 2 bins of impact parameter. So the sight lines which are less than 18 kpc are shown with the circle, and the sight lines with more than 18 kpc are shown with stars. So, and then these sight lines are color coded with their centroid velocity of the UV ionized ion, not with the H1 gas. So the velocity, color coding velocity of this is coming from the UV gas. So as you can see here, this velocity of this, the sight lines which are away from the sight lines which are more than 18 kpc, they are tracing, they have velocity of consistent with what we people found with the neutral gas from the H1 emission. So they are indeed actually tracing the strip gas coming from the stream, while leaving us the CGM of this LMC very compact, which is 18 kpc. So yeah, so with this, I would like to conclude my talk with a statement that LMC has truncated CGM, not because it's a dwarf galaxy and which cannot hold its own CGM, but it has truncated CGM because of its strong interaction with the Milky Way, and it is not an isolated galaxy. So while modeling this gas around, in and around our local group, one should take into account the CGM of galaxy, and we cannot exclude this. So yeah, this is my summary, where we have first identified the CGM of the LMC, and we said that there's a cool CGM. LMC does have its cool CGM, which is actually multi-phase. The inner region is complex compared to the outer region, and the LMC CGM is actually truncated and very compact, 0.1 of its virial radii, and this is due to its strong interaction with the Milky Way. Thank you.
Questions? There's one there.
I'm not yet constrained using this, but that is in our plan, yeah.
Thank you, super interesting. I was just wondering if there is any indications for the CGM to be consistent with either inflowing or outflow components relative to the LMC. Because, yeah, I guess simulations predict that satellite galaxies that are inflowing into the bigger host will be like bursting and ejecting winds, undergoing these cycles, and then with this sort of CGM being stripped. And yeah, just wondering whether there are constraints on that.
So if we move to this, if I understand your question, so these are for a particular ion. If you see, so if you are saying that the velocity of these absorbers, centroid velocity, this is less than the LMC velocity, and this is more than the LMC velocity. So based on that, you are trying to associate with inflow and outflow. So we have, so they are randomly distributed around the, in this I don't know like how to implement this, I mean, we have distribution of, like these sight lines shows the distribution of velocity centroid, so some could be inflowing, some could be outflowing, so, but systematically we have not looked for this signature, yeah.
Any question? Just one more. Last question.
So with the low ions you observe, I wonder if you have any insights on the ionizing mechanism of different components?
Okay, so yeah, so we did try, since we have high ion, also from like, so we did try calculating the column density ratio of the high ion divided by the low ions, and we actually find, but at this point we do not know how to interpret this, but we did find, like this is the column density ratio of SI4 divided by SI2. So you see the column density, this ratio is increasing when you are going away from the Milky Way LMC. So the ionization is increasing. So we are still probing this and still characterizing this. So maybe later we'll like significantly characterize. But yeah, when we are moving away, this ionization is changing. We do find that, yeah.
Great. Let's thank the speaker again. Okay, our next speaker is Sebastian Lopez from The Ohio State University, and we'll talk about temperature and metallicity gradients of local starburst-driven outflows.
Yeah, so hi everyone. My name is Sebastian Lopez. I'm a fourth-year graduate student at Ohio State. I work with Laura Lopez as well as all the other collaborators that we have here listed. And the work that our group has done focuses on constraining the temperature and the metallicity gradients of starburst-driven outflows in nearby systems that we can resolve out well the outflows, as well as other multi-wavelength properties. The galaxies we've done so far, and we wish to expand our sample more, but the ones we've done so far are MED2, which I'm sure you've all heard of, NGC 253, and NGC 4945. So to give some background that I can just sort of go through very quickly, thanks to our great introduction for this session. If we look at the whole baryon cycle as a whole, galactic outflows are typically in charge of ejecting out the metals and material out into the CGM and potentially even the IGM. So if we were to look, like most things in astronomy, when concerning gas, these winds are multi-phase mediums, meaning that each phase has its own set of constraints, different properties, and different responsibilities in this whole cycle. So we expect the hot phase to be the one that drives most of the wind energy, the one driving out the metals. And then the wind mass is mostly carried by the cooler phases, and some of that may fall back down in the form of galactic fountains. And along with streams from the IGM, you could potentially start over their whole star formation process. Because of the multi-phase nature of these winds, we require a multi-wavelength approach to try to constrain all the different properties and all the overall just understanding of the system. And these are all important puzzle pieces that are used to basically answer open questions such as how does the hot phase couple to the cooler phases, how does the overall wind evolve, how many metals are carried in the wind, and how is some of this material entrained. All of these are very complicated, different aspects, different open questions that all require different wavelengths. So our group specifically focuses on one of the pieces of the puzzle. We look at the hot X-ray emitting phase of these outflows. And although less constrained than its radio and optical counterparts, it's still vital to learn as much as we can from it. So shown here on the left, we have a Chandra image of MED2. In the middle, we have 253. And then at the end, we have 4945. So these are the ones we've looked at so far. And what we do with this data is that in order to constrain the properties we are interested in, such as the temperature and the metallicities and the densities, we extract spectra along the outflow. And to basically just give you an example of what that looks like. On the right, we have a spectra for one of the central regions for NGC 253. So the black crosses, that is the X-ray data, the spectra. The violet is the overall model that we use to fit the data and to constrain the various different properties. The other different lines are the various components that I'll go briefly into. And yeah, and then we also see several emission lines, and as you can see, very highly ionized material is what's found in these X-rays. So across all three galaxies, when we model the spectra, it requires a thermal plasma component. So shown here is the warm hot component in red. And then they also require a power law component that models the non-thermal emission that is still present in the outflows. So we remove all the point sources and stuff like that, so we can only focus on the gas, but you can still have some of that non-thermal emission that is present in the spectra. Some regions, typically like the central ones, in this case, have a second hotter component that we fit the spectra, and that is shown in the green hot component. And the clear indication that you need that second component is basically that iron 25 line that you see all the way at the end. That indicates there's very hot 10 to the 7 Kelvin plasma that's present there. Another important component that emits in the softer X-ray band that is shown in the orange is charge exchange. This is something that's been absent from X-ray work that was done over a decade ago. This charge exchange is actually pretty important. It can, as I mentioned later, contributes a good chunk of the total broadband emission. And what this process is, essentially, it's when an ion strips an electron from a neutral atom. In the context of galactic winds, what that means is that it's where the hot phase is interacting with the cooler phases, and that produces the soft X-ray emission. So once we fit our spectra and we find our best fit values, we can then constrain several different properties, and as the title and the talk, the temperatures and the metallicities. So for the temperature, we find that the central starburst region is about 10 to the 7 Kelvin. This is in line with that iron 25 line that we saw. And then the rest of the outflow is about 10 to the 6 Kelvin. It sort of cools as you move out with distance. Number densities are of order 0.001 to 1 particles per cubic centimeter, typically peaked in the center and a center adjacent region. When it comes to charge exchange, we find that it contributes a significant amount of the total X-ray emission. So in some regions where it's detected, it can be about a few percent to contribute up to 30 to 40% of the total X-ray emission. So that's definitely a lot, and not including the charge exchange can definitely affect things such as the metallicities that you are measuring. See Ocon et al. 2024 for a more detailed line-by-line analysis of how this charge exchange manifests in these X-rays. And then on the right, when it comes to the metallicity, so here we are able to constrain metal abundances for oxygen, neon, magnesium, silicon, sulfur, and iron. So that's what we do. The different elements are shown on the x-axis, and we divide this up between approaching and receding outflow. So the approaching outflow, that's along our line of sight, has the least amount of material that's in the way. And then the one at the bottom, the receding outflow, of course, is the one that's moving away from us. And what we notice when we're looking at the approaching outflow is that within the uncertainties, you can see pretty similar compositions between the three different galaxies. This essentially shows that there's a common origin. That's all that supernova ejecta that's fueling this wind. For the receding outflow, there's much more scatter, but as I mentioned, because of all the intervening material, it's attenuating the X-rays, and as a result, you get more uncertain behavior. So continuing with the whole metallicity abundances, while those plots that I showed in the slide earlier, those were for at a distance of 0.2 kpc, so we try to keep them at the same distance for all three galaxies so we can get an apples-to-apples comparison. But when we zoom out and we look at the overall outflow and see how these different abundances are varying, if we look at the MED2 abundances, just for an example, magnesium and iron in the middle, and then for NGC 253, which is shown all the way at the right. You can see the rest of the abundances if you look at the papers. But what we notice is that for MED2, it seems that these profiles are much flatter than they are for 253. 253, it seems that they are very peaked in the center. It almost seems like you're having issues getting the metals out of the system. And this is something that's we found puzzling when comparing these two galaxies to see what it is that's going on. So, an avenue we could go down is to see how larger scale galactic properties may influence how these metals are getting out of the system. So MED2, for example, it's considered, I think, as dwarf irregular galaxy, slightly smaller than 253, which is a barred spiral galaxy, much more similar to the Milky Way. And of course, as we've heard throughout the conference, the mass metallicity relationship tells us the lower mass galaxies have lower metallicities. And then one explanation for this is that they're more efficient at ejecting out their metals through outflows. They have lower gravitational potentials. And we look at Chisholm et al. 2018, which measured a metal loading factor, so the proportion of metals being ejected out across different galaxies of different stellar masses, and I believe this was done in a warm phase, so I think it was a UV or something. They find that the metal loading factor is much higher for these lower mass galaxies. Currently, as you can see, we don't span a good large range. We're still in that 10 to the 10 stellar mass range for our three galaxies, but in the future we will want to populate the rest of this and see how this compares to analysis done into optical or UV. Another thing we are very interested in is comparing our findings to theoretical models. So here we're comparing semi-analytical models of one in Thomson 2021. These profiles are for MED2. So the MED2 data for temperature on the left, density on the right are the X's. And then they compare it with the spherically adiabatic expansion models that are shown in the gray dotted line. So that's the most basic sort of galactic wind model that you can develop. And what they find is that the observed profiles are much broader. They don't fall as quickly as the models do. In order to remedy this, one of the things they do is that they forego the spherical expansion assumption. So if you look at galactic winds, they don't really look spherical. They're more of this biconical outflow shape. And that has to do with the collimation, either from like a ring of superstar clusters or the disk itself that forms these cones going from the different poles of the galaxy. So to remedy this, they decide to forgo that and measure the actual geometry of the wind itself as best you can with surface brightness profiles, and that is the blue line. And to get a better match, they add a physical process of mass loading, which is when the wind picks up ambient material and that's incorporated into the wind and has effects on the overall profiles, and that is the orange line that you see there. So if you are doing these sorts of theoretical models, of course 2D simulations include all these processes, but if you're doing these more simple one-dimensional models, these are important processes to include. And in the future, CRISM is a new X-ray telescope that's launched. This will have great X-ray spectra. We will be able to measure kinematics of the hot phase for the first time, so these are other things. We proposed time for it, so if we get it, it'd be great to compare it to these models. Lastly, the last thing I'll talk about in current work, not all the cool material as the wind pushes out is entrained in the wind. Some of it just gets pushed out. So if you look at this image of MED2 here, we see little clumps of cool material out to large distances. And the question is, how do they get there? How do they survive such a hot wind? So in the middle, I'm then showing, we manipulate the image a little to highlight these structures. You can see all these little clumps throughout the outflow. And recent theoretical simulations have found that actually these clouds, depending on their size, can actually survive and maybe even grow as they move out with the wind. So what we're doing here is using HST. We're going to provide some observational constraints on this front and see how that goes. So what we do is that we segment the image using blob finding and watershed algorithms to each of those individual clusters, measure each of the individual properties. And this is very preliminary work, so the values themselves might change. But so far, what we're finding is we find that these clouds are above the survival criterion predicted by simulations. Columns about 10 to the 20, 10 to the 21. Number densities of about 100 to drop down to about 10 with distance. Very kind of is on par with previous optical studies. So look forward to Lopez et al. 2024 later this year as to what our findings will be. So with that, I'll leave up my conclusions, take any questions, and if you're interested in the papers, in the different work, please go ahead and scan the QR codes. Thank you.
Questions?
Hi, very nice results. So I was curious, both for the observational and then later for the simulation, looking at how the density is dropping radially, particularly in the first plot you showed, is that steeper or shallower than 1 over r squared? I was just kind of curious if it follows kind of pure photonization or if it's much shallower.
I think the actual X-ray data it's shallower than r over squared. I think that's what the models predict, and then the actual data is you get those broader distributions.
So does that suggest that the ionization is increasing at larger radii, or it's just a combination of how all the numbers work out?
It might be that second one, but I'm not too sure. I have to get back to you on that.
Thank you.
One more question? Yeah.
I'm sorry if I missed it, but did you get a distribution on the cloud radii from your observational constraints?
Yeah, so actually I didn't show it. Because we are a resolution limited by HST, we find cloud radii of about a few parsecs in size. Yeah, so we can go down to about 1, but that's when we reach our resolution limit. I know there's a recent work that found sub-parsec scales using absorption studies. That was Zhu et al. 2024. And then I know CO finds much bigger, about 10, 20 parsecs. So yeah, there's a big range, but what we're finding is just a few parsecs in size.
Thank you.
Yep. Let's thank the speaker again.
So good Good afternoon, everyone. I'm not Leah Gozzi. She's my PhD student, and unfortunately, she can't make it to this meeting because she did not get a visa on time. So you get me, her PhD supervisor, instead. So we're going to switch gears a little bit to go to colder temperatures. We're going to talk about some new results on the molecular phase of the circumgalactic medium. And since this is a star formation conference, I hope it is obvious why we want to understand the molecular phase of gas, because that is intimately linked to star formation. And we are presenting a case study in brightest cluster galaxy, the BCG, of a well-known cluster that is called MAX 1931. So I'm not going to spend too much time to motivate you why we want to understand the CGM, because the previous speakers have already done so. But I think in the particular case here, where we are studying the galaxy in the center of the galaxy cluster, it is of particular interest because the BCG typically could have AGN episodes. And this AGN could be sending gas outwards, but this gas that is being sent out, some of them could eventually fall back down into the CGM, the BCG, in order to fuel the central black hole as well as star formation back. And we think of it as a cycle of feedback. So studying the CGM, in particular in the molecular gas phase, could help us better understand the whole feedback cycle and how it works. So a bit about this case study of why we choose this particular BCG. So this is a composite image where the blue is showing you the Hubble H alpha and nitrogen 2. And this particular galaxy is situated in a cool core galaxy cluster, and it's been well studied with ALMA and also Hubble, where some interesting peculiarities are found. So what is special about this BCG is that unlike normal BCGs, it is pretty star forming, and it is pretty rich in molecular gas. So in terms of star formation rate, it is forming star at the rate of 250 solar masses per year. And in terms of stellar mass, it's pretty massive, 6 times 10 to 11 solar masses. And it also contains a radio loud AGN, so perfect site to study how AGN feedback works when we have already a lot of molecular gas. And what is interesting about this source is that it has an extended circumgalactic medium tail that is seen in molecules, so seen in both dust continuum emission and also in CO. And this is done by deep ALMA observations presented in Fugate et al., where you're looking at the radial profile of the different dust emission and the CO, and this tail extends to 30 kiloparsec. So we figure it would be a good chance to go after it with JWST to understand what the warm molecular gas is like in that tail. And what is another thing that is particular about this CGM tail is that it has very low gas-to-dust ratio. The gas-to-dust mass ratio is 10, which is an order of magnitude lower than the typical value for Milky Way. So we're interested to follow up on this source, also to understand if there are any particular astrochemistry happening in that CGM tail there. And so we wanted to know if this tail is particularly gas-poor or dust-rich. And this actually is the motivation for going after the source with a single-dish observation in a submillimeter. And the reason being, ALMA is an interferometer, so it is not very good at picking up extended gas emission. So we wanted to go after it with single-dish observation in order to see if this molecular CGM is actually spanning a bigger scale than picked up by ALMA. So we combined existing archival observations presented in Fugate et al., which already has a decent set of 3 CO emission lines with some new observations. So I mentioned single dish. So we went after it with APEX and also the Nobuyama telescope, which goes after 2 CO transitions as well as atomic carbon. And some people would argue that atomic carbon is a better tracer than CO in terms of the molecular gas mass measurement, and that is because it is a simpler transition than CO. And so we go after this, and we also obtain some new observations with JWST with the MIRI medium resolution spectrograph. So this is something that we are going to show in just a bit. So first of all, just to understand the geometry of this system, this is plot of the 3 CO transitions with the ALMA observations. So here, the grayscale image is showing you the Hubble UV images. So you see that there is a lot of star formation, but this star formation is clumpy. It does not look like a typical BCG at all. And the contours are showing you the CO, where it looks more clumpy, it is untapered, and the red contours are taper CO emission. So you see that the molecular gas can be a bit clumpy out in the CGM as well. And so what you're seeing here, the three plots, we are looking at the CO spectra of the three CO transitions, and that is the flux versus velocity space. And what you find here, and this work is, like I say, presented in Fugati et al., where all the three CO lines, they have a similar velocity profile. You have the brighter peak at the systemic velocity of the BCG, so this is gas within the BCG. And then you have another weaker component of molecular gas that is tracing the CGM, and is redshifted by 300 kilometers per second. So what do we find with the single dish data? So what we find here, to summarize, this is the Nobuyama spectrum, and then this is the APEX spectrum. So the Nobuyama is picking up the CO 1 to 0 line already observed by ALMA, and we find basically the same flux here in the Nobuyama spectrum as in ALMA. So the conclusion being drawn here is that indeed ALMA has picked up all the molecular gas in the CGM, so we are not missing flux by going it with interferometer. And then with the APEX spectrum, the green one is the C1 line, where you see the same two components, and then the orange line is a CO 7 to 6. So we are quite limited by signal to noise here, so we don't really see the second CGM component in the CO spectrum, but it is seen in the C1 spectrum. Right. So what do we do with all these nice CO lines? That is something that we can do, which is that what we're showing here is the CO SLAT or CO spectral line energy distribution. We are really looking at the line ratios compared to CO 1 to 0. These are the different lines. So the BCG SLAT is shown in red, and the circumgalactic medium that you saw before is shown in orange. And we compare to other literature galaxy types. So what we find is that the molecular gas in the BCG is quite excited. It peaks at CO 4 to 3, and that is on par with local ULERGs. And this is, again, unusual in the sense that normal BCGs don't form a lot of stars. And what we find with the CGM here is that it is less excited. It is peaking at a lower transition of CO 3 to 2. So this is just a way to visualize the CO. And remember, we have also the atomic carbon transition. So we can do something a bit fancier than just looking at SLAT here, where we apply a code called RADEX. In case that is not clear, this is basically a standard method that we use to model molecular gas transitions. So we make assumptions that that it is a large velocity gradient, and we also assume non-LTE transition. But basically, it is a code that does radiative transfer modeling. So the input here is that we put in all the line fluxes of the CO and the C1 transitions, and we try to infer the gas properties in terms of three parameters: the number density of molecular hydrogen, the kinetic temperature, as well as the virial parameter. So fast forward, this is the result of the covariance plot of these three parameters. And we're showing the BCG and the CGM component separately. And what you can find is that here, in the number density versus temperature space, this is where you can clearly see that the gas in the BCG is hotter compared to the CGM in terms of number density, which you can see more in this histogram. We have less constraints there directly, but it appears that the CGM is peaking somewhat at lower densities compared to the gas in the BCG, which makes sense. And then in terms of the virial parameter, we just don't have very good constraints, so it does not look super good. But I think at least from this covariance plot, it is obvious that the gas within the CGM is, has different gas properties in the sense that it is cooler and also less dense, which makes sense if you think about that. So moving to the next part, I mentioned JWST, and I want to use some brief motivation to talk about why we want to use JWST to look at the warm molecular gas. And here is an example from very, very nice work towards the Stephens quintet. It is a galaxy group that is compact, and the blue contours are showing you the molecular hydrogen lines seen with Webb. And you can see that actually most of the warm molecular hydrogen gas is found in the space in between galaxies. And why is that? That is because this warm molecular hydrogen gas is tracing shock fronts and also turbulence. And here is a nice cartoon from the same paper where it is saying that, or it is trying to illustrate that as the shock front propagates through diffuse gas, it can change the phase and density structure of the clouds where the molecular gas could be falling into smaller clumps. So we wonder if we could see the same, because this target, we find a lot of star formation, so maybe there's something there. So we got some Cycle-2 MIRI MRS IFU data, and we are still analyzing this. This is all quite new results, and this is animation prepared by my other grad student, Lucas Kuhn here. So what you're looking at is that within the MRS observations, we can see we target two of the rotational H2 lines. This is the S5 line. So we are looking at the continuum subtracted cube where you saw clearly the BCG that has a lot of warm molecular hydrogen at the systemic velocity. But you also do see the same tail that you saw in CO that follows a quite complicated structure. It is not just a line, but it's clumpy and interesting. And then we have a lower energy transition, the S1 line, and it pretty much follows the same structure where you see a lot of gas in the BCG, but then you also see the tail that is kind of curling through, and that follows a similar structure as the CO. And you see the same in the 1D spectrum where you have the BCG at the systemic velocity and then a redshifted peak that is redshifted by about 300 kilometers per second. Okay, and well, just quickly, I don't have time to show this, but in the MRS data, we also detect a lot of things that are interesting, ionized lines like here, and also power features. And those are super interesting, and I would love to talk more about it, so please come find me. And just this very last plot here, we are showing you the same warm H2 results compared to the ALMA CO, which is shown in the black contour. So you do see that the warm and the cold molecular gas are tracing the same regions spatially. Kinematically, they also follow very similar patterns. So we are currently still analyzing what to make of all these results, but we do have detections. And I'm going to leave you with my summary, and I'm ready for your questions.
Really nice talk. So I was wondering, have you made a map of the second weaker component that you detected in C1 and whether that associates with the plume or any of the ionized gas maps?
Talking about the atomic carbon, right?
Yeah.
So that is unfortunately single dish data, so we don't have the
dish.
spatial resolution, but we are proposing for ALMA observation. So if we get the time, I can tell you in a few years.
Very cool.
There's one question there. It's the last question.
Do you see the pHs at the same location of the tail that you see in the molecular gas?
Great question. Actually, yeah, we do see power clumps outside of the BCG, and that is something that really intrigues us. So come find me, I can show you.
Great. One last question.
Hi. Yeah, I was curious about the shock fronts you were finding in the interaction, and do you have any estimate of the Mach numbers of those shocks that actually leads to that sort of the densities required for that fragmentation in the pre-shock regime?
So we are not that far in the analysis yet, but yeah, that's something that we hope to be able to answer, and I'm happy to chat.
Yeah, definitely.
Great. Let's thank the speaker again. So I think it's time for flash talks. So if you are scheduled for a flash talk in this session, please come by.
I think we can either that or we can use this one too. That works. You can choose to use this one too, either way.
It's easy to go there and show.
Sorry?
It's easy to just go there and show. With this mic, I cannot do that.
Go ahead.
Each flash talk will be 2 minutes. So,
Hi, I'm Ishita. I'm doing my PhD at IUCAA, India. And my poster is about the CGM around galaxies at redshift 3 to 4. So they are very low mass continuum faint galaxies. We detect them by their laminar alpha emission in Muse fields. And we are particularly interested in this redshift range because, like we know, around redshift 2, the cosmic SFRT had a peak, and since CGM plays a big role in star forming activities, so we just want to know what was happening in the CGM at these redshifts. So our survey Muse Cubes has 8 bright background quasars, and these sightlines are probing the CGM of the foreground galaxies. So in this result section, I have just tried to show some of the interesting results that I have found so far. So in this section, I'm showing that for C4 and H1, both the cases, we found that the covering fraction is higher when the galaxy is situated in a group environment compared to the normal, like isolated field galaxies. And then over there in that corner, I'm showing that this H1 covering fraction also anti-correlates with the rest frame equivalent width of Lyman alpha emission. So the equivalent width of the emission should be higher when the galaxy is gas poor. Otherwise, the photon will be destroyed by the radiative scattering effect. So kind of this plot is trying to give us a picture that when the galaxy is gas rich, it is also situated in a medium which has lots of cool gas. And then finally, in this section, I have tried to focus the fact that from my absorption line analysis, whenever I'm finding the really strong H1 absorption systems, they are found at higher impact parameter, almost always beyond the virial radii of the galaxies from our survey. So, so we were just thinking, okay, maybe we are just missing the true host because they are very low in mass, so faint. But then I was also interested to know what is the metallicity of this absorption system, and while doing that, I came across one of the systems that I'm showing there. It is extremely metal poor with a metallicity of minus 3.6 times solar metallicity. And more interestingly, it is actually sitting in a, it is associated to a group of 7 galaxies. So maybe in some of the cases, we are just probing the pristine gas from the filament structure, or maybe the pristine gas